Hi, welcome to video lecture 8. My name is Fatih Kırshanlı and today I'll be continuing to talk about social interactions. More specifically, I'll be concentrating on experimental economics and multiple equilibria concepts. About the social dilemmas, as you can remember, sometimes self-interested individuals generate good outcomes. We have seen this in invisible hand games. And sometimes self-interested individuals generate bad outcomes, and we have seen this in Tragedy of Commons games and Prisoner's Dilemma types of games. And social dilemmas are everywhere, as we all know. About this, now we can talk about the work hours as a prisoner's dilemma case in this situation. If you recall from Unit 3, we assume that individuals choose their work hours independently. But the choice of work hours could be a strategic interaction as in Unit 4. In this figure, as you can see in your left, in which the names Bala and Anil are very familiar to you from my previous video lecture, suppose that Anil and Bala like short work hours, earning a relatively high income, and this could be modeled as a prisoner's dilemma. And as you can see in that regard, 2, which correspond to 8 hours, is a Nash equilibrium and a dominant strategy equilibrium. You should also remember what Nash equilibrium and dominant strategy equilibrium mean. For that, you can either go back to my previous lecture or you can read these concepts from the book. As you also remember, in the previous lecture, I talked about how we can resolve the social dilemmas. Experimental economics shows that social dilemmas can be sometimes resolved by social preferences like altruism, repetition that harnesses reciprocity, and through institutions that punish bad behavior. In your homework 1.4 or the extra credit assignment 1.4, you analyze how these facts transform a 2x2 prisoner's dilemma. When it comes to social preferences, we know that an individual has social preferences when they place a value on what happens to other people, even if it results in lower payoffs for themselves. Social preferences can help people solve social dilemmas. What are some examples of social preferences then? Altruism, reciprocity, inequality aversion, and spite. For that altruism-related questions, you're going to have some specific examples in your homework 1.4b. How do social preferences affect the economy then? For that, I want you to think about this. Families, collective action, wage setting, and tax compliance for a minute. You can stop the video now and then think about this for a minute and then evaluate the situation yourself. When it comes to economic experiments, we know that economists generally cannot and shouldn't perform experiments on entire economies. Economists increasingly use lab experiments to test their theories. Economics experiments investigate social dilemmas like public goods game, ultimatum game, and these experiments shed light on how social dilemmas can be solved, social preferences, repetition, and institutions. Let's talk about an example for a public goods, but before that, let's talk about what public goods are. As you can see in the figure on your right hand side, this introduces the taxonomy of public goods. Please get familiar with these concepts by watching this video, continuing this video, or reading your book. Public goods are non-excludable because everyone benefits from them. Non-rival because one person's use of goods does not diminish the benefit of others. Public goods are one of the 4 types of goods. Public goods are susceptible to free riding, and self-interested people tend to under-contribute to public goods. Public good experiments in terms of repetition. Life is not a one-shot game. In repeated games, players have an incentive to cooperate today to encourage others to cooperate in the future. A tit-for-tat strategy performs very well in repeated games. Tit-for-tat strategy means play whatever strategy your opponent played in the last period. And repetition initially raises contributions. In this figure on your right hand side, you are seeing the contributions of the cities to a worldwide public good experiment in terms of periods. As you can see, in initial periods, the contribution is much higher than the later or upcoming periods. So the contributions fall in later rounds. And the reason behind that, if you ask why, you're going to have questions for that related to repetition can resolve a prisoner's dilemma as in homework assignment 1.4c. What about public good experiments in institutions? Subjects were given the option to pay $1 to subtract $3 from another player. How do you think peer punishment affects average contributions? As you can see in this graph on your right hand side, you can get an answer for that question in the initial periods and the later periods. Why do subjects punish low contributors? This can be because of subjects may be driven by social preferences to enforce social norms, or subjects may benefit from punishing others if it substantially raises contributions in a repeated game. A combination of social preferences, repetition, and peer punishment generates high contributions. And sometimes we see that the government punishes bad behavior, in which you're going to see some examples in your homework 1.4d. After talking about public good experiments in repetition and institutions wise, there is one worldwide known economist about who we need to talk about. Elinor Ostrom trained as a political scientist but won the Nobel Prize in Economics in 2009 for her analysis of economic governance, especially the commons. She studied how communities use common resources without succumbing to Harden's tragedy of the commons. Ostrom distinguished between common pool resources, rival non-excludable goods, common property resources, goods managed by communities. Ostrom is famous for her law that a resource arrangement that works in practice can work in theory. Also, one of the most important information that I can provide for you about Elinor Ostrom, she is one of the two Nobel Prize laureates in economics as a female economist. After that, in 2019, Duflo won the Nobel Prize in Economics. We can also talk about sharing economic rents in that regard. There are often mutual gains from cooperation, as in grazing game, prisoner's dilemma, public goods game, and people commonly attempt to negotiate a cooperative outcome, like in Montreal Protocol labor contracts. Also, sometimes these negotiations break down when an actor believes the mutual gains are being shared unfairly, as we see in Kyoto Protocol or in quits, firings, and strikes. In that regard, we can talk about ultimatum games. In an ultimatum game, there are two players, and in which two players must agree on how to split $100. The proposer may offer the responder between $1 and $100. The responder can either accept the offer, in which case the proposer and responder each get their share, or reject the offer, in which case neither player earns anything. What does this payoff matrix look like? As you can see in that figure in your or kind of matrix in your right hand side, now you can pause it for a second and think about this question. What is the Nash equilibrium in this game? And the answer is 90 and 10. About the ultimatum game, there is one important information that I need to share with you. So far, in all type of games, we have analyzed simultaneous games. However, ultimatum game is a sequential game. That means we sequential games are sometimes represented by a game 3, as you can see on your right hand side. A game 3 tree clarifies the order of play. What would you offer? What would you reject? Or what would you accept? What about field experiments in economics? We know that economists also conduct field experiments. Parents are sometimes late to pick up their children from school, for example, and this tardiness is costly for schools and teachers. In order to actually experiment this, Israeli parents actually they were charged $3 for each that they were late. What do you think happened after the fine was introduced? As you can see from the figure on your right hand side, after the fine introduced, the number of average uh, the average number of parents who are arriving late increased. Surprising, isn't it? Why is that so then? It seems that fine crowded out social preferences. Parents would rather pay $3 than feel guilty for arriving late. For crowded out as well as crowded in terminology, please read your book carefully and get familiar with these terminology. Also for field experiments, you can watch the video of Professor Juan Camilo Cardenas about invisible hands working together. And as you can see, after all these examples that I've tried to provide in the previous video lecture and this one, social dilemmas are everywhere. For example, in a party situation, everybody's dominant strategy is to stand up. When everyone stands up, people do not see better on average than when everyone sits, and standing is unpleasant. We can actually demonstrate that in a model in a 2 by 2 game. In this matrix form, you see we talk about, or we actually uh, uh, we see sit and stand together. Now pause the video for a second and then find the Nash equilibrium in this matrix. The Nash equilibrium is 5, 5, which stands for stand, stand. And stop the video again and think about for a minute about the social optimum. And the social optimum outcome in that matrix is sit, sit, which is 10, 10 payoffs at the end. After we have talked about all these social dilemmas, now we can talk about multiple equilibria games. The games we have studied so far have had a single equilibrium. That was because both players had a dominant strategy. In Invisible Hand game, in Prisoner's Dilemma, in Public Goods game, we all had one single equilibrium. In many games, both players' best response depends on the actions of the other player. At an Nash equilibrium, everyone is doing the best they can, given everyone else's strategy. We expect to observe Nash equilibrium in the world. Otherwise, someone has an incentive to change their strategy. In that regard, we can give an example like in driving on the left hand side of the road or the right hand side of the road. In the world today, people drive on the right hand side in some countries and they drive on the left in others. Although overwhelming majority of the countries people prefer to drive on the right in their countries, both conventions are Nash equilibria. And we can illustrate this in a 2 by 2 game. As you can see in this matrix, each player's best response is to copy the other. The Nash equilibrium in that regard are R and R, right and right, and L and L, left and left. And the payoffs for these are 2, 2, and 2, 2. When we talk about another example about our very famous people Anil and Bala, we are going to talk about crop choice redux. Consider Bala and Anil's crop choice when these are their payoffs, as you can see in your right hand side. What are the Nash equilibria? If Bala grows rice, Anil will grow cassava, which will correspond to 4-4 outcome. If Bala grows cassava, Anil will grow rice, which will correspond to 2 payoffs each. Which equilibrium would we expect to see in the world? If players choose their crop independently, they could get stuck in the bad equilibrium. This is a social dilemma because both players are better off at the other equilibrium. There is no conflict of interest here because both players are better off when they specialize in their comparative advantage. The same argument can be made in the language choice. What are the Nash equilibria in the matrix on the right hand side? Players could choose Java and Java and then get 4-3 outcome, or players could choose C++ and then they get 3 and 6 payoffs respectively. There is a conflict of interest between these Nash equilibria. Why? Astrid prefers Java and Java, and Bettina prefers C++, outcomes. Is one equilibrium objectively better than the other? Yes, C++ outcome provides for a higher total payoff than Java and Java. However, both equilibria are efficient. After providing these examples, I want to specify some other games in which about which you will encounter while doing your quiz 1.4. In the first example, you're seeing a type of assurance game with conflict where movie and dance are the outcomes. In the second example, you are seeing 4-2 and 2-4 are two equilibria is a type of chicken game. And in the last game, you're seeing 4-4 and 2-2 are an assurance game without a conflict. After actually talking about assurance games with conflict and without conflict, I should tell you that assurance games in reality are ubiquitous. And assurance games, like in reality, they are everywhere. Assurance games helps us understand whether people drive on the right hand side or left hand side of the road, code in Java or C++, type on a Q keyboard or Dvorak keyboard, find friends on Instagram or Glassboard, speak English, Chinese, or Esperanto, follow or break the law, support or undermine social norms against theft, dishonesty, and cheating. So, after talking about assurance games, now I would like to provide an example or two examples, in fact, about the public goods game. In a public goods game, in this example, there are two players. Each player receives $4. Every $1 contribution makes to get them 75 cents for both players. We can represent this in a 2x5 game. As you can see, the figure or the matrix form of this in your right hand side, Row's dominant strategy is to contribute 0, and column's dominant strategy is to contribute 0 as well. So the dominant strategy or equilibrium is to play 0-0. However, the equilibrium is inefficient because both players would get $6 instead of 4 if they played 4-4. But this game is a little bit complicated. Now let's move on to another example in which we are going to have or we can abstract from some details to better highlight the logic of a public goods game. Let's restrict player strategy set to just two strategies. Contribute $0 or defect. Contribute $4 or cooperate. What does this game look like? Here it is on your right hand side. Now you can stop the video for a second and think about what is the Nash equilibrium in this game and why. As you can know, the Nash equilibrium is 4-4 in this game. DD, defect, since neither player has an incentive to change their strategy, which means a Nash equilibrium. Does the game illustrate a social dilemma? The answer is yes, because both players will better off at CC. What is the name of this kind of a game? This is a prisoner's dilemma. So as you all see, we have covered almost every important concept in social interaction so far. So before conclude this unit, I should tell you that social interactions can be modeled using game theory. Individual self-interest leads to mutual benefit in the invisible hand game, mutual losers in the prisoner's dilemma. Social dilemmas are sometimes avoided due to social preferences like altruism, repetition that harnesses reciprocity, institutions that punish bad behavior. Also, conflicts of interest can also arise over how mutual gains are shared, as in the ultimatum game, which equilibrium is chosen, as in the assurance game with conflict. Before closing this video lecture, I would like to